Okay, so we're going to do some boring stuff tonight. Communication again, but I'll try to go as quickly as possible with it, so it doesn't get too boring. So let's start from here. So we're going to be talking about signal attenuation and how to deal with it. All right. So let's start. So basically, what happens is when you start sending a signal down a cable, two things happen to it, right? Whenever you send a signal, two things happen. Number one is it gets attenuated. So attenuation. And number two, what happens is it picks up noise. So two things happen. So when that happens is you can actually see this here. It's somewhere written along here. You have attenuation. Attenuation is gradual signal power reduction. And noise. There's also a definition of noise. Noise is random unwanted power. Unwanted power present that adds itself in a random manner to the signal. This unwanted random power is called noise, right? So that's basically what noise is, right? So we have attenuation and we have noise. So basically what happens is this is a signal that you get at the end of the cable. And then when you amplify it with a repeater, you get a noisy amplified signal. So basically what happens is it's not really good. If this was your television, you get a lot of static. If it's your radio, you're going to hear a lot of crackles. If it's a picture, it's going to be very grainy. So basically this is the problem. So what we do is actually we don't try to do this too much, because if you were to repeat this cycle a number of times, like get this, then cover a couple of 100 kilometers, and then it becomes noisy again, amplify it, and then it becomes more noisy, and then you amplify it again, and it gets more noisy, and this thing just keeps going on and on and on. At the end of it, you're just going to get a lot of trash. So that's why we don't prefer using this method of sending analog signals. That was actually one of the limiting factors for analog signals. So what we actually do is, instead of taking analog signals, we turn them into digital signals. So how do we turn them into digital signals? That's what you have to talk about. But the digital signal is basically either it's a 0 or a 1. So 1 is basically on and 0 is when it's off. So this is a really easy signal. If you take this signal, a digital signal, which only has two values, 0 and 1, if you transmit it, the same things do happen. You do get attenuation and noise here also. So you get this as a result. But you can still differentiate between this being a 1 and this being a 0. So basically it's the same signal, it's barely readable, but it still has that information. So what you do is, instead of just amplifying this, we regenerate it. And regeneration of the signal creates a brand new version of that signal, which actually matches up. And as a result of this, you don't end up having the noise. You can transfer this over infinite distance and you don't lose any data. Right, anyway, so this is basically the thing about analog and digital signals, and that's why we don't prefer analog signals, even though analog does look better before the transmission. For example, remember those old photos you used to take on your film cameras? Mm-hmm. Have you ever used a film camera? Mm-hmm. The ones where you wind it up and then
negatives.
Yes, you have negatives and stuff. So you never talked about number of pixels, because that resolution was almost atomic. Basically, the chemical reactions which used to happen on the surface of the film caused the image to be formed. So even if you could, if it was focused well enough, if you took a picture of a tree, if you take a magnifying glass, you'd be able to see the pattern or the details on the leaves of the tree. Basically, there's no limitation of megapixels because it's so high resolution. But the reason we don't use it is fundamentally because you won't be able to transfer that data and keep it safely. If you lose a little bit of it, it's gone, it's noise. So that's why we shifted into digital cameras, right? Digital cameras are easy to transfer, easy to store, and that's why we actually shifted to that, even though it had less resolution than one of those high megapixel cameras. So going on into all of that, so we can actually see advantages of using a digital code. So how do we exactly copy this into a digital format? So what we do is we have this 4-bit system where basically we have, say, for your A levels, you need to know about the 4-bit system, which is basically divided into ones and zeros. Zeros and ones, you have these 4 values. So what can they be? There's basically 16 possibilities. Do you have ICT? Mm-hmm. Then you should know this. Have you heard of this?
Not at all.
Really?
Maybe I'm just a bad ICT student.
No, you're just joking, aren't you? This is 1. Next one will be 0001. Then it will be 0010. 0011. Then it's going to 0100. 0101. What? 1, 2, 3, 4, 5, 6, 0, 1, 1, 0, right? And then you go 0, 1, 1, 1, right? So you can go along doing this, blah, 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 blah,
Till
blah,
we
blah.
reach 111.
Yes, until you reach 1111. So you'd end up getting 16 values, right? So what you do is, obviously, if you're splitting a value of, say, 0 to 16 volts, 0 to 16 volts, then a value can either be 0 or 15 volts. 0, or it can be 1, or it can be 2, or it can be 3. It can't be like, 1.4, right? We can't do that. So what we do is we always choose the whole numbers, right? So what you guys need to do is you need to read through all of this. There's a lot of detail here about how we use it, and there's this thing about the most significant bit and the least significant bit. So these are basically the first and the last values in your binary code. And basically there's also this concept of sampling size. So basically, how frequently do you take a sample and then send it off down as a signal? So that's going to be something that we also need to figure out, right? So the frequency of sampling. So all of this is done in this process called analog to digital conversion, and that's what I'm going to show here.
Is that an ADC?
Yeah, that's ADC. That's right, man. That's right. You kind of know stuff. You should be proud of yourself. So yes, this is basically what we're talking about. Say this is an original analog signal. So as you can see, it's smooth, which represents this an infinite variation of the voltage. Starting from 8, it slowly varies and gradually increases to 14, and then from 14 again it slowly decreases down to somewhere around 2, and then back up to 8 again. So if we were to pick any value, then the value itself would actually be anywhere it is. Right? It could be anything like 10.2223, or even like 12.5556. So lots of random values. So notice how this has been converted into this. So what happens is the 8 becomes 8, the value around here becomes 12. So they sample the value every 125 microseconds. And as they sample it every 125 microseconds, you got a series of these values. All right? So this is basically what happens. So a few important things that you have to keep in mind here is, because we're using a 4-bit signal, there's a possibility of up to 16 values. Number one. Number two is the sampling frequency, which is 124 microseconds. So basically that gives us approximately 20 kilohertz for its sampling rate. So that means we can go up to that value, as far as I remember. But an important thing is, if you want to sample something which is 20 kilohertz, then you need to take something a little more than double, right? So basically, if you're sampling a signal which has a highest frequency of 20 kilohertz, then you should sample at a rate of above 44.1 kilohertz, basically so that you can actually pick up when it's double, right? There's a lot of detail in that, but I'm not going to go into that detail, because what you need to know is the sampling frequency has to be higher than double the frequency that you're wanting to choose. Right, so that's that. So these are the basic concepts that we need to know before we move on. Am I missing out anything here? I don't think so, but yes, please study all of this, read through all of this, so that we have nothing to miss out on. So going back to this, what we're going to see is we have a bunch of values. So they vary over this range, and we sample them into these values at the same time period: 0, 125 microseconds, 250 microseconds, 375, 500, 625, and so on and so forth. Then what happens is each one of these is represented by a binary code, and you can actually use your calculator to find these values. Do you know how to use your calculator to find these values, Mukta?
No.
Serious?
Hey, sorry.
Without calculator, let's show it to everyone. I haven't actually tried this on this calculator, so I don't know myself. So usually we go, oh my god, this is all in pictures and stuff. So yes, basically base n. So we give 3, yes. So this is decimal, right? So say for example a value which is 12, right? So if we want it in decimal, we just write 12. Then what we have to do is we have to convert it to binary. So how we convert it to binary is there's supposed to be a button here. Isn't there a binary button somewhere here?
Bin lekha.
Bin. So basically, why is it blue? Any reason why it's blue? There we go. We're binary, right? And then we press equal to. How do you convert this to decimal? Yes.
Hey chat, help us.
There we go, decimal. So it should be like that. So let's try again. So 12 in decimal is this, and binary of this. Oh yes, there we go.
Okay.
All right. So basically 12 will be written as 1100. So you can shift in between the two, right? So, well, actually I haven't used this calculator for this specific function previously, so that's why I'm not really smooth at it. But see, as you can see, 12 here is 1100. So you don't have to actually write down the entire list and go on. For example, let's try 3 volts. 3 volts should come in as 0011. So we go to decimal, or just decimal press. You go to decimal, and then let's write 3. So this is the value in decimal. And if we want it in binary, we just press binary, and we get, as you can see, 0011. Right? So that's basically how you convert from binary to decimal. Let's try one more value. Let's try this value, which is 8 volts here. So basically we go back to decimal and we write 8. So the decimal value is 8, and then what we do is we convert that into binary, and that is 10000, and that's exactly what we see here. 8 is 10000. So yes, there's an easy and quick way that you can use your calculator to actually do all of this stuff. I'll have to reset mode. How do you reset mode on this thing? Man, I'm so confused.
How about I do this?
Done. I guess so, yeah. Right, guys. So basically, this is the signal which is sent down the cable, and the delay between each of these signals is 125 microseconds. So you send the 1000, but when you send it, you have to actually tell the system which one is first and which one is later. So basically, that's how we do it. So yes, you send the 1, then you send the 0, and then you send the 0, and then you send the 0, and then you tell them that it's all together, computer, and then it's like, oh, all right, so it's 1000. So what does that mean? It can be converted into 8 volts. So what happens is when this digital signal is transferred along the cable, this is when we get the benefits of this whole system. So basically this is the benefit that we get, and we use this benefit exactly at this point when we convert this signal and send it down a cable. So when we do this, we get basically this sort of combination of values. So 1000, 1100, 1110, and this is actually analog. Right?
Okay.
This is poor level analog. And why is it analog? It's because we're seeing the values coming in like this.
And not just 0 and 1.
Yes, exactly. So how do we make the signal better? How do we make the steps smaller? There's two things we can do. One is increasing the number of bits that we have in our code. The more the bits are, the steps become less difference in height. The height between them decreases. So instead of 4-bit, we actually never use 4-bit. We use stuff like 16-bit. Or 32-bit, or even 64-bit. So those have a huge number of combinations, like 2 to the power 64 combinations. So that basically allows us to send a lot of information, except for values from 0 to 16, right? Or 0 to 15. We can send colors, we can send letters, we can send symbols, we can send a lot of things, and we can send them much faster. So that's why basically that's one of the things we use. And another thing we do is we can make the steps smaller. How do we make the steps less wide? We just increase our sampling rate. If we sample at a higher frequency, the steps become narrower, and hence the signal gets better quality. So yes, that's it. That's for analog and digital signals. Yes.
So currently we're sampling at what?
125 microseconds.
So আরো wide করতে হলে কি like
আরো wide করতে যাবা আরো narrow করতে যাবা so তখন you say sample at 100 microseconds or 100 microseconds or 25 microseconds, right? So that makes the steps become smaller. But the width of them decrease and the height of them decrease if you increase these values, right? So that's basically how you do this. There we go with that. Moving on, we're left with one last thing, and then we're going to be done with communication actually, is the concept of decibels, all right? So the thing about signals, and when we send them along really long cables, or when we send them along up and down satellites, they change by huge numbers. Like, the value changes by like say 100 million and stuff like that. So what do we do in that case? In that case, we no longer use linear scales. We actually use logarithmic scales. And the reason we use logarithmic scales is a two-time advantage. As one advantage is basically because if we use a logarithmic scale, it's easier to represent the data, right? So basically, the ratios would be easier to represent using decibels, number one. And the second advantage of using logarithmic scales is if the cable increases in length, instead of multiplying values, you just add the logarithmic values, which makes the maths much more easier to work with. So one of the things we do is we use the concept of how strong or weak a signal becomes based on bells or decibels. So if it's bells, log P1 by P2, for example, is a representation of this. And number of decibels is 10 log P1 by P2. So usually we don't even use bells because the unit is way too large. So we end up using decibels, where basically 10 decibels is 1 bell. So the equation that we use is this. Number of decibels of increase or decrease is 10 log P1 by P2. So what is P1 by P2? So if we take, for example, this cable here, P1 is the signal which comes out, and P2 is the signal which goes in. So the difference between the two is a representation of how much the signal attenuates or basically loses its strength. So we do this calculation by using 10 log P1 by P2 and do the calculation and find the value. And if we don't do this, what happens is the values are way too large to work with. An important thing that you need to remember is you have to use a little bit of common sense when you use these answers or questions. For example, P1 will have a much smaller value than P2 does. So if you put this into this equation, it's going to give you a negative value. So if it gives you a negative value, that basically means the signal is being attenuated. Mistakenly, if you put P1 on top and P2 on the bottom as a denominator, then what's going to happen is it's still attenuation. That doesn't change the truth, but the value will no longer be negative. It's going to become positive. If it becomes positive, you need to understand that it's positive because the value which is going in is higher. The cable is still attenuating. It's still losing energy. So they did a sample experiment, a sample working here, that the amplifier has a gain of 45 decibels, which means what? It increases the signal strength by 45 decibels. So it's going to be basically what? The power out is going to be more compared to the power in. So power out by in will be a positive value because you're amplifying it. So they're saying the input power is 2 microwatts. So look at what they did. 45 decibels is equal to 10 log power out by in. They place the value, substitute the value of the power in, and if you do the math properly, you get 6.3 times 10 to the power minus 2 watts. So that is basically a value which is 45 decibels more than 2 microwatts, all right? So that's a very easy way of doing it. The next thing you can see here is that you have a certain length, and we find out, say, it attenuates by a certain number of decibels. Say it attenuates 100 decibels. So if it attenuates 100 decibels, and say this cable is, say, 20 kilometers. So that means what? It attenuates by 5 decibels per kilometer. So that's attenuation per unit length. And that basic example is shown here. Basically, you have that going on. How do I convert 5-bit digital numbers into decibel numbers? You don't need to know that, really. Let's just move on. All right. Then, the input power of a cable of length 35. A 5-bit key, nobody uses 5-bit.
Yeah, all I know is like powers of 2 to
4-bit, 8-bit,
4, 8,
16, 32, 5-bit, 6 hexadecimal use kora hoy for certain cases.
hexadecimal hai
but colors and stuff. But I don't know more detail about that. But 5-bit, I've never heard of 5-bit.
hexadecimal to je actually tell us colors.
But I have never heard about 5-bit signals.
I never heard of 5-bit.
Anyway,
Although my knowledge is limited.
Mine is too, in that specific manner, I must admit. Right, let's move on. So the input power of a cable length 25 kilometers is 500 milliwatts. The attenuation per unit length is 2 decibels per kilometer, right? So basically, how much would you lose? 25, 2 decibels, so you're going to lose 50 decibels, right? That's basically the first step of the working. Calculate the output power from the signal. So 50 decibels down for 500 milliwatts, 500 divided by P out is equal to 50, and your calculation should give you 5 microwatts, all right? So then they're going to talk about signal to noise ratio. Basically, if you have a 5, basically if you have this sort of attenuation, this next thing is, if this is your signal, how loud can your noise be? Or if your noise has a certain value, how loud does your signal at the end have to be so that you can differentiate between the two? So let's just read through this bit and we'll be done. The signal cannot be allowed to travel indefinitely in the cable because eventually it will become so small that it cannot be distinguished from background noise. An important factor is the minimum signal to noise ratio that effectively provides a value for the lowest signal power allowed in the cable. In the above example, the background noise is 5 times 10 to the power minus 13 watts and the minimum signal to noise ratio is 20 decibels, which means what? The output has to be 20 decibels louder than the noise at the end of the cable, where PM is the minimum signal power. So they basically do this calculation and they get the minimum power is going to be 5 times 10 to the power minus 11 watts. After that, this enables the maximum uninterrupted length of cable along which the signal can be transmitted to be determined. So if you can lose up to 120 decibels, that's basically a calculation between this and 500 milliwatts. And then they see that's basically 120 decibels, right? 510 power minus 3 divided by 510 power minus 11, 120 decibels. And hence the maximum distance is going to be 60 kilometers. That's it. So these are the major questions that they ask in attenuation, and I believe we are done with communication. So yes, we'll move on to another chapter. Most likely I would like to do CT scanning tomorrow. So we'll talk about CT scanners, and if we can, we'll drop in X-rays too. I'll figure that out and let you guys know.